Okay, hello everyone. I think we can start. Uh, so, my name is Jacek, and I may admit I'm kind of shy person and a bit of introvert, right? And why I'm actually speaking that before starting presentation. So, no one spoke about that, but I really would like, if you remember one thing about my presentation, maybe that'll be this one. That you know, being on this side, it's kind of very unique experience, and I really encourage you guys to think about that, to become a speaker, to think about the topics you may present, and come here and speak. I'm pretty sure there's lots of interesting things you work on, and I'll be very glad to hear about them. So please think about that. Being on the side is kind of cool and kind of a unique experience. So I really recommend. And yep, so let's start my talk. I'll be speaking about event streaming in Revolut. And firstly, what's Revolut? So that's a company I'm working on, and what we do, we are doing e-money services, so kind of banking services, and we mostly take care over some monies of our clients and give some services that banks do, but we try to do better and faster. And this is not actually conversation about Kafka. And interesting thing is, like, many people ask me, is that about Kafka? Is that what you use? And it's not. So sorry for that. But the actually thing is, we do something different, and we can achieve the same stuff in better for us way. So I'm kind of glad I can share this information. And actually, I'm pretty glad there was a lot of conversation about events and streaming itself, because that was a good baseline to understanding some of the concepts here. Okay, so as usual, there is Slido. If someone has questions, please put them to this site. On the end, I'll be just going and answering any questions you would have, if time will allow. And that's a few bits about myself. So, yeah, my name is Jacek again. I worked in a few different companies, mostly within financial markets, although I started with a little bit different company. The interesting thing is I started with a .NET Word. I'm on Java conference, how could be? So yeah, I started with .NET and C#, and then after 4 years I switched to, and almost till now I'm focusing on the Java world. I did some open source. Some of them are kind of nice, and databases, object database you can use in .NET Word. It's kind of, I always wanted to know how to create object database and why they didn't popularize. So I kind of know now. And two other projects are, one is about how to set up possible trading office, how to make it scalable. And another one is kind of open source competition for algorithmic contest platform where you can have a fun with. And the last thing about myself, so I really consider myself as an enthusiast of all the things we do, and I always kind of had my favorite stack, besides of the fact that I was actually, that was my main stack. I was kind of in love in JavaScript for quite some time, but then yeah, kind of things change. Then I switch a bit more like to Kotlin. I still do Kotlin development. Actually, some parts of the things which I'll be showing you were done in Kotlin. But recently, kind of my interest is more of the Golang, but mostly about some choices they made, and yeah, some interesting things happening there, which probably we'll be observing. So, okay, to understand this things, the technical side, it's very crucial to understand actually what's the context we are in. I already mentioned you, we are a financial company, and that's actually putting some constraints of what we do and how we do. And money, so we deal with money, and as you may imagine, this is highly regulated market. So all the banks know it for quite a while. And why is regulated? you probably recall the crisis in 2007. That are the reasons why it's regulated. So we want to make sure our monies are safe, they do not disappear. And this is actually putting us in the, we are in the place where the domain we deal with, the part which is related to the money, has to be correct, has to be always correct. And there are different mechanisms to deal with that. Another kind of part of the context for us is rapid growth. So for those of you who know Revolut, you may know that we are around 4 years old company, so fairly young, and we have lots of customers. That was kind of huge growth of the scale for us. And this is actually connected with some needs for dealing with all the requirements for the users, delivering features. So it's like you keep the same features, you adding new, but there is another dimension of complexity coming in, which is connected with the growth. And those are the things you should have in the mind, but I'll be showing technically how we actually deal with them when you consider processing events. Why? So whenever you do software development, so whenever you create some product, you always should ask the question why. Why you do that? What's the value you want to provide? And for event streaming we created, there was few things which we had to consider. Why we want to create, why we need it, why we need to add some complexity. So firstly, we want to be always correct, right? So that's one side. And on the other side, highly available. This is like a bit conflicting. So we had to solve this problem. Another thing, the events or data we keep, they have to be durable, but this is like really, really durable. And in here you have example that is more than 10 years. So it's kind of a thing to remember. We treat our events immutable. It's nothing kind of new. Usually people do that. But one thing which we considered and our solution allows us to do and actually still develop on that is be able to do fairly advanced queries on the consumer side. So we didn't want to limit the way of how consumers deal with events. So we wanted to allow them to actually tell explicitly, ideally in some declarative way, what am I exactly interested in? And that's something very cool to have. And yeah, the last thing, which is scalable with ever-growing amount of events environment. So we only kind of grow and we have to deal with all those events considering all those requirements. And there is a bit different dimension actually to look at the same requirements. So this is more, I name it like technical view of some of the parts. So strong consistency. Again, this is about the correctness. We have to be correct, right? So sometimes for some parts of our domain, eventual consistency is acceptable, but for some, not necessarily. And things like at least once delivery, high availability and scalability, those I already mentioned is like similar or a bit different language. But another thing which is kind of crucial for us is low latency, because we started to split some part of the system. And you know, if you are in monolith or if you are in a single service, you're in process, right? So everything you do via method calls, object invocation. So it's kind of pretty easy, which we consider like no time, right? Once you start going to microservices, and this is actually, I will repeat what some others say, it's like you rarely or never should start from microservices because there is a cost you pay for, and no one wants to pay that cost besides if you don't have enough value for that. So you really want to pay off this cost of paying it. So low latency for us is kind of crucial in terms of distributed systems. So you want to keep control over, so it's not even like going just now with all possible effort to limit latency to the lowest possible amount. It's more like having ability to control latency, which is kind of hard, but it's doable. and have ability to lower down whenever you need or if you need. So that's another thing I'll be speaking about. How did we actually approach and how we solved that. Persistence, and the last one, which I didn't mention in previous, but it's kind of becoming ubiquitous and obvious if you're in highly distributed systems, and microservices are kind of. This is observability, and for us it's very crucial to actually understand if something happened, where it happened, why it happened. So can I actually know something before an incident happens? Can I know if my performance degrade of the service, right? So this is something which again we need to consider. As you kind of see, the ML requirements is kind of big, and there are solutions which gives you that, someone might say for free, but it's not exactly like that. So instead of developing things and growing on the problems you want to solve, that's what we did actually. So we have custom, let's say, solution where we grow with the problems appearing with the needs, instead of taking something like, I know, Kafka, which is just like big step and it's already solving all the problems and bringing you all the complexity connected with maintenance of that, configurations, keeping it available and all that parts. Okay, so yeah, so let's go to some details. This is the design of the solution which we created. So the interesting pieces are, we use Postgres for some part of that, actually for storing data and listen and notify mechanism. And why it's good for us, because we already use Postgres in all other services as a storage. We have a knowledge about that. We know what kind of problems may happen there. And it's giving us ability, which I mentioned you before. We have requirements for having ability to do advanced queries. So if I have something like Postgres or in a relational database, I may do almost kind of all kinds of queries I may imagine. I just need to model them and allow to subscribe using this advanced model. So that's something we wanted to have, and that's something we'll be utilizing more and more. Another thing which you may spot in here is we don't have like n or thousands or hundreds or tens of instances of the services. We have two Postgres instances. So we have master and replica plus backup, of course. And we have two instances of this event store application, which is stateless application, which is responsible for orchestrating all the events movements. But we have just two of them, and we have just two databases. Someone may ask why. That's because this is serving all our traffic. It's doing pretty well. We are observing how much capacity we have, and this still give us ability to horizontally scale if we need. Simply, we don't need yet. That's kind of the right side, and you may see on the very bottom there is the way how we set up our application. So we always we use Google Cloud Platform, and we use virtual private clouds to separate networks between different parts of the system. And here you may actually see that the storage side is decoupled from the application side, which is actually decoupled from the API gateways and all the things which are exposed to our users. So that's, let's say, server side. In the middle, the symbol you see there, this is GCP, Google Cloud Platform load balancer, which is a load balancing between those two event store instances. And on the left side, we have kind of microservices clients, but this is more like a show of use cases we have, because obviously we have n times of different business services serving different needs. But from the perspective of our event streaming, that doesn't matter that much. Mostly what matters is the use case they want to serve. So the obvious use cases are producer and consumer. And in the middle, there is something a bit kind of trickier, or maybe actually not trickier, but slightly different. So besides of producing events and consuming events, which is kind of the streaming we wanted to have, we have ability to just query for events via fetch mechanism. So you do just synchronous queries because, for example, you like to read events data based on some requirements. The interesting thing here is, and that's what I'll say a little bit later on too, is we use, so on one side, this event store application, which is in the middle, this is something which exposes REST endpoints, and we do expose REST endpoints for all our services, but this is not like API or REST first approach. We more prefer to develop SDKs, and especially in this case, it was important because there is lots of complexity coming into the client SDKs, which we wanted to be avoided. So we don't want our consuming services to have actually implement. They obviously can, but rarely they should, and this is not always obvious how to do that. So we deliver SDKs for our services, in this case for publishing, fetching, and streaming. And thanks to that, the services may very easily integrate with our event store solution. Things which are worth to spot is like this event store implementation is totally stateless. So we keep state with Postgres, which is good with keeping Postgres, managing data, and by itself, event store is written using Kotlin. So that's the piece I was mentioning about the Kotlin, and we use, this is interesting, if you don't know it, there is a framework created by JetBrains, it's named Ktor, and it's cool because it allows us to do asynchronous processing of incoming requests. It has ability to inject WebSockets too, so actually we use WebSockets to do streaming back to services. And another interesting thing about Ktor is that you can plug whatever engine you need. Maybe not whatever, but there is few available, almost all performant ones. So we use Netty on top of the Ktor with some coroutines from the Kotlin. It's not Kotlin talk, but for those of you who recognize them, you may imagine that it's giving us quite a good throughput with fairly low amount of threads needed for processing them. Okay, so let's go next. So this is the that was the design of the solution we have, and you may see here few of use cases, real use cases we use it for. So audit log of user actions used by customer service. So whenever some actions happens and we want to recognize, especially monies and everything which is related to money. I know doing some manual transfers or rolling back some transactions, everything has to be logged, and some our support actions with user money or user data, this all has to be logged. So this is actually a mechanism which giving us this possibility. Another thing is all those things I've said to you, this is used for our let's say I name it like operational part of the system, but besides of that we have data engineering team. They use Kafka, by the way. And they actually plug into our event streaming solution, take events to their way, and then consume on their own. They have some machine learning algorithms which help them to do a risk scoring model, and based on that we can do fraud detection. There's fairly complex topic, I just knew some high levels of that. Another thing we use it for is like, for those who knows Revolut, you probably use it most often for currency exchanges. And for those who don't know, that's actually our main feature, that we allow to do FX exchanges with intra-banking rates, right? So kind of cheaper or much cheaper sometimes than you usually would do with banking cards or some other ways. But the thing with that is whenever we have transactions, we need to almost in real time, it's obviously not real time, but as quickly as possible, monitor all transactions coming in into us or through our system, so we can actually know what kind of risk we have to hedge against. Hedge against, what does it mean? So hedging is a kind of mechanism in finance to, for example, in this case, to just buy the opposite position. So if you have currency from USD to Euro, you usually do vice versa in another direction to limit the risks. So this is another case we use it for. Real-time P&L, so it's kind of booking ledgers. So what's that? So if you have like books of your spendings and you like to know that all the money you had and all the movements of money and final result of money you keep, this is actually correct. That's exactly what it is about, and thus again I'll be repeating another case where we have to keep all our data super correct or correct. This is because we simply don't want money to go. And yeah, automated marketing campaigns and promotions. So we can consume events, observe some patterns, behaviors, and based on that, we can do some automated campaigns and promotions, which is another thing. It's not all use cases, although I think those are one of the major ones. Another interesting thing which we do recently is like when we, especially now going to decouple more and more microservices, because we are in the position when our original services they go to the limits of the capacity they can serve. So we had to start thinking about splitting some domains. The problem with splitting of domains, which you could actually hear repeated a few times, is usually it's connected with distributed transactions or sagas, how some people say or describe previously. And we need to have some way to deal with that. Usually, we don't want to do fully asynchronous flows, because if you use a mobile app and you do something, you really want to know that transaction settled fairly quickly, or if it's not. Why you want to know? Because users are used to behaviors or to how system works now, right? So if you had some services being or operating with many different actions within the same process, and the solution worked fairly smoothly, you like to keep the same behavior. So that's what we want to achieve, and how we do that. So whenever we split the service, what we do is like we can do synchronous call, but there is network partition between services. So what we can do, so few things. I mentioned that we treat events, okay, maybe the other way. So our actions or this transaction processing, we have to make it idempotent. Idempotent means like if you do it or run it a few times, it will give the same result. Why is it important? We have a lot of retries. We have lots of possibilities to fall back if there is any failures, especially if you have distributed system. And imagine this call to second service, which I've described previously. It didn't fail, but there is network partition. The problem with such cases is that you never know if it succeeds or not, right? So what we do is, so we like forget in this part of processing. So this is like synchronous flow. We forget about that, but we have always fallback mechanism, which is like consumer observing on the events, and if the events come, which is like half or internal states of transactions. So this consumer, if it's observing such events coming in, is able to do the necessary part of the work which wasn't done. And so you may imagine that actually it succeeds, and the fallback mechanism will get the event. So in both cases, you may run the same action. That's why it's pretty crucial, not only mentioning this retries in single place, that's crucial for us to make actions or any processing we do idempotent. Okay, so let's move to the next slide. Yeah, always correct. And actually that is, I think, the most tricky part about how to do that, because even if you use mechanisms like Kafka, RabbitMQ, or any kind of messaging system, you have to solve somehow this problem. And there are two solutions you may do. You may do event sourcing. So you firstly generate event, and then you do all the necessary processing. But remember what I said previously, we want to keep the behavior, or actually user experience of application same as it was when it was like in single process. So this solution doesn't work for us, and we had to go into other way. When you change the model, and based on the model, you generate the event, and now you have like two separate things, and you have to keep them consistent. So if you roll back one, you have to roll back another one. If one succeeds, another have to succeed too. So let me tell you how do we approach it. Okay, so first thing, persistence. Firstly, if you want to have system consistent, you have to persist it. And we have actually few, okay, every part of the flow or every part of the service has own database. So every microservice has own database, and even store, which I showed you previously, has own database. So what we do is when you are in the producer, in the flow of a producer, instead of sending events, so we have a model. Model is changing. So let's imagine new transaction is coming. We create transaction. We have our own Postgres database. So what we do is actually at the same database, we name it like, or contextually name it like a journal or something like that, or log event. We do within the same transactions save of the model and save of the event. So we know that transaction will succeed, or it will roll back, but it will roll back both, or it will save both. So once we succeed with our model change, we have saved into database or event. Then what we do is like we just asynchronously process this events. So we send them with retries, with all the possible mechanisms which guarantees us delivery as long as we need, and that give us ability to have this consistency. It's not as that simple as I just said, because like we have then few levels of asynchronous sending and guaranteeing that it was sent. Because firstly, you may imagine that this asynchronous send of the saved event fails. You have to still do something with that, right? So we keep the state in our journal database or table within the same model database. If event was marked as successfully published or not. And this is all happening asynchronously. So whenever we get 200 response from event store, we can mark in this table that event was successfully published. Then on the left, you may see that there is the small watch, which is actually scheduled jobs, which is checking about all the events which were marked successfully, and we just clean them up. That's actually keeping this table fairly small. We can, with automated way, manage the size of it, and querying and saving to it. It's with quite nice time, which is fulfilling all our needs, which works pretty well. Okay, so then the same event, once event store gets it, it's saved into event store database. And finally, what we use the mechanism from Postgres, which is named listen notify. This is pretty nice and very simple mechanism. It works in the way that you may at any point of time do notify Postgres. So during the insert to Postgres, you may notify that something happened, some event happened. And what we do is like whenever event is created, or written to database, we keep it like a log. So we only add items. We doesn't update. We do not update them. We trigger events which contains the full event message. So all applications event store, the previous which you saw, they can listen on those events, take them from Postgres, and then based on the subscriptions coming from our consumers, decide if to send or not. And this is interesting, and that'll solve many of our problems, because imagine we have this event store is stateless instances. So you may write to any of them, but then subscriptions coming from consumers may actually go to any of them. So you have like, you may have concept. So Postgres is doing this kind of synchronization for us, and whenever you get the event and it's notified, Postgres notify all the instances of event store. So then doesn't matter which event store you subscribe to, all of them will get all events notifications. And yeah, actually I didn't mention it on the consumer side. This doesn't always happen because there are different heuristics. We give a lot of, I would say, flexibility to our consumers to decide how they want to approach dealing with duplicates and dealing with reconnections. So you may imagine there is few mechanisms like, you start getting events and your processing of events is slow. So we use some back pressure mechanisms using some queues, and at some point the queue may be full, so we interrupt WebSocket connection, and based on that, once you finish your queue, processing of the queue, you have to decide from which moment of the time you want to roll back. We use we use date, which is actually set on the insert by Postgres, which is cool because it's actually ordering our events across the date on every transactions, which allow us to come back at any point and get back the events from the moment when we reconnected or where application just went down. And two solutions which people do is some use just redis and just store in the redis the last date of the event they seen. Or another approach is to just store snapshots. So you may kind of do copy of this data and store them, but still based on this data and processing of it, you will need to decide, at least in our approach, what is the last date you would like to roll back from or actually reconnect from. Okay, this is becoming, so this is another view on the same. In a bit more details. So you may actually see that this processing is a little bit more complex. So there are numbers to actually help to understand how it's going. So whenever event is published to event store, we have this fallback mechanism running. Actually, if we have, for example, 3 applications, let's name them A, B, and C, which produces or publishes transactions. So they store transactions, and as a part of that, they send events about them. So now I actually take the context because we sometimes have small services using a dedicated database for some context, but they share this database. Still, because one table per service per database is, we believe, overhead. But what does it mean is like for those 3 applications which share database and they create similar events, we just need one of those applications to become, we name it a reconciliation runner. So we use some locking on the publisher side, which allow us to just choose one instance of the publishers to become this reconciliation process. And this is actually rescuing all the events. So it's going through just this log table and checking which events weren't published or actually weren't marked as published after 1 minute and resending them again. And this is doing as long that as we have some leftovers in this table. And this is actually guaranteeing us that at some point this event will be published, and yeah, then all the observability of that comes to mind, and we do our best to actually monitor how the system is behaving. So how many events is transferred just after model change versus how many events is reconciled, so rescued, because they couldn't be published in original call. That may happen, for example, because of the timeouts. So databases become slower at some point, or something goes with hardware on GCP, it happens, or actually those machines they give, and then you may get some timeouts and you need to rescue from those situations. There are some optimizations we do, like the reconciliation process. Instead of doing event by event and sending event by event, we send batches. And why we send batches? Because if you have batch, you may do insert to Postgres database in much more performant way. So instead of doing single node many times, you just do one big, and you gain quite good performance on that. Okay, so let's move on. Yeah, so some requirements and how we achieve them. So those will be quick because I spoke quite a lot about them. So this is actually how we achieve at least once delivery. So at any point of the time where you are in the flow, we do retries. If something goes wrong, we do retries. In the places where we cannot do retries, or there is some possibility that even retries will fail, we do like background processing, like this reconciliation, which I mentioned to you, or you may say like rescue processes running in the background, which observe what's the situation, and based on that, they do another kind of retries. Okay. Persistence. So what do we actually do with Postgres? So we use the newest Postgres, which is giving us few nice features. One of those things is partition. So you may imagine our current tables for events has more than 4 or 5 terabytes, I think, and that'll be ridiculously slow if we would like to process such a big table with any queries and subscriptions. So what we do, we partition our events based on the actually on monthly basis. Currently, this is working well, although we monitor closely the situation, because with this grow, it seems like the amount of events is going faster than linearly. So it's kind of something we probably pretty soon need to rethink about. So monthly partition will not be enough, and possibly some sharding will be required around those monthly partition in terms of how we split the data to make it faster and make it scalable. Notify list mechanism I already mentioned, and yeah, we use master-slave replication. So all the queries, so all the fetch sites, so sometimes we like to just fetch some information, they go against replica, and starts actually taking all the load outside of the master database. Okay, let's move on. High availability and scalability. So going deeper into that, those things I already mentioned to you too, right? So we do stateless services, asynchronous processing, we use Cater, Netty, coroutines in Kotlin for server side. But things which people don't mention, and we use both scaling. So it's not only about horizontal scaling. We need to remember that it's much, I'd say even sometimes cheaper, because the cost of maintenance if you start horizontally scaling, it's much bigger. But being in GCP, it allows us to increase amount of CPU, increase amount of RAM, and it's much easier than starting horizontally scaling. So we have both capabilities, and we can clearly calculate which is more convenient for us and do both sides. So we still have a lot of capacity thanks to that, and that's working pretty well for us. Low latency, and yeah, there is lots of things we can do in here, and things which we already do. So from those which we already do, all the processing is done in boundaries of single region in GCP. So region is like I know, single city, as far as you remember. In Google Cloud Platform, there may be few zones, and zones would represent probably different buildings, but that's giving us very high performance. So Google is optimizing heavily network connections within the regions or within the zones. Things like obvious HTTP connection pooling. So whenever we on the SDKs do some calls via HTTP, we utilize pools of connections instead of creating every time new ones. We do asynchronous logging because we do a lot of logging. So this kind of distributed systems with SDKs give us lots of variables, and it's very hard sometimes to understand what's going on with the system or what happened with the event. So we have to use a lot of logging and monitoring systems to actually understand at any given point of time what's happening in the system, and if there is something wrong happening with some event, we want to understand where it's stuck and what it happened. Another nice feature that actually Google Cloud Platform is giving us is internal TCP UDP load balancing. So they name it like that. They have very specific load balancers within virtual private clouds. So if you are in the boundaries of that, you may use the throughput load balancer, which are really high performant one. They do a lot of engineering for them, and that's something we use and working pretty well for us through TCP in our case, obviously. Immutability already mentioned, so our events are immutable. We only add them, and our event log, so the database on the publisher side where we actually firstly store that, it's immutable too, and we process that. Yeah, it's not immutable. That's kind of a mistake, because we changed the state of the events in this publisher, so we actually put in the journal change the states from unpublished to published, and we delete them. So this is actually a mistake. Okay, and yeah, client SDK. I already mentioned you that we use that to make life of our developers easier and to control all the hard problems like concurrency, logging. We run in our SDKs, client SDKs, health check background runners, which kind of observe what's going on with, for example, subscription, with publishing mechanisms, with reconciliation, and frequently reporting on that. So at any given point of time, you may actually just check logs or check the monitoring system for giving publisher or other parts of the system and understand what's going on. We keep it like in DSL way, so here you have example where you just do like event persister with configuration with asynchronous publisher, and the only thing we do then is persister save and action event represents our event, which is sent then to event store. Fetching, a bit more complex and already showing some capability of filtering. We only use fairly base queries for now because there is lots of changes happening there, and we still don't need yet to utilize fully advanced queries. That's kind of the work we soon plan to. But there are two main names where it's when we would like to describe events is like the model for event, which is for which event is generated, and event type. So considering those two, you may build a query which then goes to database, and then you fetch, in this case, all events related to account which were actually balance changed events. And query looks like very friendly for developers because they just do event query from, they put whatever necessary to take data they want. And the hardest part of that is kind of streaming, and there is lots of engineering done in the background of how to concurrently deal with WebSockets and make it retriable, safe, reconnecting. But mostly what you have to do as a user, you just specify the consumer and you specify your subscription. So to subscription, you pass concept. In this case, you may see we just pass lambda, and there is a method latest timestamp to reconnect from. So this is the concept I mentioned to you. You will have lots of reconnections, lots of interruptions of failures, and you like to reconnect when you stream events from event store. And to do that, you dynamically pass the time from which you'd like to reconnect. Filter already mentioned, and consumer, we then just start subscription and it's doing all the job. Challenges. So things which we have to consider, or we want to consider for the future, is like achieve P99 latency of less than 20 milliseconds. Quite hard to achieve, but there are some ways or ideas we may do. The things which I describe here are mostly connected. Actually, they are for both for database and for processing. So potentially we may switch to binary serialization protocol. We use JSON now, it works well, and it doesn't require to change us a lot of stuff, so there is no problem with it, but we have some spare space here to improve. Another thing is like we use replication between database, master and slave. But what we may actually do is we may split the clusters to save and to read and make them optimized for read and write. What does it mean? As example, if you like to have Postgres optimized for a write, you remove all the indexes. So you remove all the indexes, and then at every insert, you doesn't need to rebuild them, you doesn't need to update them, and then only you need to plug some replication mechanism, which is actually bringing down the data to replicas, and then you build all the indexes on the replica. That's something we may do. We didn't need yet, but again. And for most of the communication, we use HTTP. We may actually, we were already measuring, and with HTTP2, at least calls becomes twice faster, although there is overhead, for example, with certificates and dealing some stuff. Actually, it's making just the code more complex. We didn't need it yet, but potentially in the future, we may consider that. Another thing which we need to consider is event schema. So for those careful of you, you saw in consumer that we have just model event class. It's fairly generic, and we keep events. They are of course different under dynamic object, and dynamic objects can be queryable in different ways. But you need to be roughly aware what you should query for. The plan is for future to do some more advanced mechanisms like event schema, which allows you to do all the stuff like versioning, discovery, auto generation, and be technology agnostic. Now we mostly focus on the Java with some parts in Golang and Python for data engineering team, but that's kind of mostly considered as a Java. Database scalability, already mentioned that. We may do some denormalization, regional sharding, and some other type of sharding. So we still have some possibilities to improve our database side. Okay, and just quickly wanted to show you how the example monitoring looks like. So if you actually look on that, that's how our New Relic page looks like for event store, publishers, and some of the consumers. So we monitor quite few things. One of the things like received events, of course, obvious stuff like utilization of memory and CPU per hour event, store instances. There is one interesting thing which may be slightly different. So this listen notify mechanism within Postgres, it's keeping the queue, which may become full at some point. So it's fairly important to monitor that, because usually if that's becoming full, it's 8 gigabytes, as I remember. There is sign of some blocking and problems. So we didn't have much of that, but still we want to be aware. And yeah, there is much more. So for example, we measure a latency of the saves is usually between 25-30 milliseconds, although you need to remember that with this kind of metrics, firstly, there is some sampling happening. And another thing is that some of the saves are quite bigger because they represent batches. So you may remember that our reconciliation is doing, it can actually take quite a few events and save them during one insert, and such insert will become a bit bigger. Yes, so that's this piece, and yeah, we do quite a lot. I probably would need another 1 hour to just discuss all those items. Okay, coming back to presentation, and yep, just last thing, if anyone is interested what we do more, you may find our booth just next to the exit, and we're hiring in Krakow too. We have offices in Krakow, in Russia, and in London. So yep, you may find lots of exciting and interesting roles though, including like in my team, we do in platform engineering lots of quite challenging and fairly technical stuff. Okay, so that's for the presentation. I don't know if I still have the time. It's like 0, so I have like no time, right? So yep, that'll be it. Sorry for not answering your Slido questions if there are some. Thank you very much for listening.